All right, ladies and gentlemen, class recording has started. So, last week, we started talking about electric charge. And we said that electric charges come from where? Subatomic particles, right? And we talked about the similarities and differences between electrons and protons, right? They're similar in that they're both subatomic particles. They're similar in that they have the same relative charge, and but they're different in that one's positive, one's negative, etc., etc., etc. While those are individual charges, we talked about charging, right? And we said an object becomes charged when it has an imbalance of subatomic particles. So if something has more electrons than protons, it has a negative charge. More protons than electrons has a positive charge. But it gains those charges depending on what happens to electrons, right? We don't ever move protons. We can move electrons between one object and another object, right? If we have more electrons than protons, that means it's gained electrons. More protons than electrons doesn't mean that it gained protons, it actually lost electrons. And that's because of the whole idea of conservation of charge, right? That if we have one object losing electrons, another object has to gain electrons so that the total amount of charge is conserved, all right? Then we talked about ways that that can happen. We talked about, right, charging involves an interaction of objects where we have an imbalance of protons and electrons, gains, loses, but it deals with how we get those objects to gain or lose electrons. So the first method we talked about was friction. Friction involves movement, right? Movement of two surfaces past one another. The second type of charging we talked about was conduction or contact, right? And we talked about grounding with that sort of charging where we can transfer electrons to the ground. And then the third type of charging we talked about was induction. And we said that the key with induction is that we don't actually end up with an imbalance of protons and electrons. We just move them around within our object. Okay? Good there? Sound familiar? All right. Friday. We introduced, oh my goodness, what happened? Oh, I remember what I did. Friday, we introduced electric force. We talked about the idea that charged objects can exert forces on each other. And we know that because oppositely charged things do what? They repel, they push each other away. Oppositely charged things don't do that. Oppositely charged things do what? They attract each other, right? Sorry, my bad. But like charged things will repel each other. That's force. And we talked about that Coulomb's law talks about how much force there is. And we talked about the idea that force is directly related to the size of the charges, but inversely related to how far apart they are. And we said that it was an inverse square relationship because d is on the bottom of this fraction, but it's being squared. Yes? Okay. And here, I drew a little picture for the other class that you guys didn't see because we didn't go in that direction. Here is a hand holding a black rubber rod that has a charge. All right, it looks kind of like a French baguette, but yeah, but that was my impression of that black rubber rod that you guys charged up. So it's negatively charged, and remember when you brought it close to the water, it made the water stream bend. Right? That sound vaguely familiar? Okay. Water, somebody in the other class asked, does that mean water is charged? And the answer to that is kind of. Water is an example of induction where we have like within the water molecule, certain sides there's more electrons in certain parts and more protons in other parts. We'll talk about that more when we get into bonding. But we talked about that, okay, if you hold the charged rod 1 inch away from the water stream, it bends this much. But as we move the charged rod farther away, the water stream bends less and less, right? That's the inverse relationship. But when we talk about how much less it bends, right, remember d is on the bottom of that fraction. So when we look at how much force there is, It's 1 over the distance squared. So in this case, we went from 1 inch away from the water stream to 2 inches away from the water stream, but the water doesn't bend half as much, it only bends 1/4 as much. Because it's 1 over 2 inches squared. Okay? David, go ahead.
Would it still bend if the rod is less than a mile away?
Technically, yes, but the farther and farther. So David asked, would it still bend if we said like this rod was a mile away? Technically, yes, but if D is 1 mile, right, and we're squaring it, so now it's 2. Not 1 squared isn't 2, but it's one. If we have 1 mile in inches, right, that number squared, there's a really big number on the bottom, right? But if the bottom of a fraction is really big, what happens to the answer of that fraction? It's really small, right? So technically, yes.
Would it still bend if it's on the other side of the universe?
Technically, yes, right? The answer was if it was on the other side of the universe. Technically, yes. But you also have to keep in mind that if we have this rod 1 mile away from this water stream, or on the other side of the universe from this water stream, there's lots of other things in between this rod and this water stream, right? So if we could just isolate those two, yeah, it would move so small that it's hard to notice. But technically, yes. But if there's other things that get in this space between the rod and the water stream, they would affect that water stream even more than that rod might. Does that make sense? Okay. But to answer your original question, if we move it a mile away, would it bend the water stream? Technically, yes, but it's so small that it's hard to pick up. All right, good there? But then, right at the end of class, we got about the discussion of field theory, right? Or the idea that the charged rod makes the water stream move even though there is no contact between them. So scientists at the time are like, wait a second, how does it happen? How can we make something move, speed up or slow down, if there's no contact between them? So we had to come up with an explanation for that. And Michael Faraday comes up with this idea of a field theory. So a field is an area, right? A field is an area around an object where it can affect other objects. And we refer to that as the force field. And we said that it works for any kind of force that can make things move without contact. Those being gravity, electric charges, and magnetism. Right? So that we live in the Earth's gravitational field. And that's why when we toss this ball up in the air, right, it slows down and it speeds back up, even though the Earth isn't actually touching it. Okay? Good there? We generally represent this field with arrows. So, if we had to draw the gravitational field of the Earth, it would look something like this. So first, right, yeah, Earth, yes. There's Florida might be a little out of proportion, but that's what. So why don't oh wait, hold on. Western Hemisphere. Let's see if this works. All right, ready? Oh. Yeah, I gotta finish that blue circle there. So. All right. Here goes nothing. Yeah, not bad. I'm actually I'm actually kind of impressed with myself. I might actually just call it a day right here. So. I know. All right, so we use arrows to represent the field. And the arrows represent what would happen to an object in that location. The gravitational field of Earth is pretty easy. What does gravity do to every single object? Gravity pulls things which way? Well, it's down for us, but it's towards the middle, right? So here, if we had to draw the gravitational field, we would draw arrows that look like this. Because no matter where we are, objects get pulled towards the middle. Okay? Now, there are some things that we can talk about, right? That as we get farther away from the Earth, gravity actually decreases. Okay? Although that's not why astronauts float in space. We'll talk about that at another time. Okay? It's not because there isn't gravity in space. There is, right? Just don't want you to walk around with that ignorance for the, at least for the next couple months until we talk about it. But so this is the gravitational field of Earth. But drawing an electric field is a little bit harder because of this. Oh. Alright, so let me draw another awesome picture of a person. That's their thumb. And there's their fingers. And there's their magic wand. I should probably complete their fingers like this. Alright. Oh, I should probably complete the rest of their hand too. So there we go. Yeah. There's their baguette, right? So, but all right. So negatively charged, right? Now we know that if this is negatively charged, right? Let's say we bring an object that has a positive charge towards that rod. What's going to happen to that positively charged thing? It's going to be attracted, right? So we would draw a field line that looks like this. But if we have a negatively charged object, what's going to happen? It's going to get pushed away. It's going to get repelled, right? So, which one's right? Does the field come towards the object or does it go away from the object? Well, it's hard to say because it might depend on what else is going on. So the way that we do that is we use field lines. And the question that we have to answer is, what happens to a positive charge? That's always how we draw the field lines. Okay? What would happen to a positive charge? So I believe you guys have these two pictures, yes? Down at the bottom, okay? So the first one on the right, that's labeled little a. That's a positively charged red object, right? So what would any positive charge do if we brought it close to that positively charged red object? What do positives do to other positives? They repel. So if you notice, all of the arrows representing the field in that location push away because positive charges would be pushed away. Remember, the field is an area. It's the space surrounding this. And if we put any positive charge in that space, it would push positively charged objects away. But little letter b here, right? That's a negatively charged blue object. What do positive charges do around negative objects? They are attracted. So you see all of the arrows point towards that positive or that negatively charged blue object. Okay? That's easy if we only have a single charge, but if we start putting multiple charges together, red is still positive, blue is still negative. If we put a positive charge anywhere in this area, even though there's two objects, right, that positive charge is going to be pushed away from red and pushed towards blue, right? So you'll see that the field lines all point from red to blue, because that's what a positive charge would do in that spot. Okay? Does that make sense? On the right, where we have two positive charges, notice all of the arrows point away. I'm sorry, can you guys see those? Or can you see them on your outline? Do you see the detail enough on your outline? These are kind of small. Okay. All right? In this case, where we have two positively charged objects, no matter where we put another positive charge, they're always going to be repelled from everywhere. Right? Does that make sense? David, go ahead.
What do the lines look like if you put two negative charges?
You tell me.
They would repel both. How would you draw it?
That's a tough
It
one.
looks like they're pulling each other together.
Yes. So, maybe that shows up on your quiz tomorrow. I'll leave that one for you guys to think about. All right? So, so this is two positive charges, right? Okay. In general, like it says on this slide, right? It says the arrows or the lines, which we call the field lines, move away from positive charges and towards negative charges, right? So David said, well, let's talk about this picture a little bit more, right? What do you see right in the middle of those two positive charges? Empty space. There are no lines in that space. Why? So if we put a positive charge, let me do this. If we put another positive charge right there, what happens to that positive charge from this one? Or what does this positive charge do to that positive charge? It repels. What is this positive charge to that positive charge? It repels. So we have one that's pushing it this way and one that's pushing it that way. What will happen to this charge in that space? It'll stay there. Because one's pushing this way, one's pushing that way. They kind of cancel each other out. That's why there's no lines in that space. Okay? Does that make sense? At least for this picture? Okay? Lewis, question or are you good? You're just stretching. Okay. All right. Done. Good. Well, what we're saying is those lines represent what would happen to that red dot that I added to the drawing. Okay? That's what those lines are representing. If I put it here, right? This one repels, so it would just like move off in this direction like that. Okay? Does that make sense? That's what these lines are representing. Now, let me bring it over here. Right? If I put it in the middle of these two, red is pushing away, blue is bringing it towards it. That's why the arrows go from red to blue. Does that make sense? That those arrows represent what would happen to a positive charge if we put it in that space. Right? The field is a space that surrounds that object. Do good.
Why does that look like a magnet?
Because a magnet has a positive side and a negative side, except we don't call it positive and negative on a magnet. What do we call it? North pole, south pole. So magnetic fields look very similar to electric fields, because we'll find out in our next unit, electricity and magnetism are very related to one another. It deals with the same concepts and the same things happen. What? Gravity's a little different because gravity can only do what? What does gravity do to other objects? Gravity always attracts, and that's why a gravitational field always points in one direction. The gravitational field around the Earth would look the same as the gravitational field around the sun or the moon or whatever. Yeah, I know. I drawn fast on there at the bottom. Okay, but electric fields and magnetic fields look a little different because they can both attract and repel. Okay. All right. Good with those ideas? Okay. All right. Let's transition here, and let's take a look at the new outline that I gave you today, which apparently I didn't pull up. Done good. Yep. Positive charge. Yes, that's the big idea, right? That's why I made this red dot, because we said red's representing positive in this picture. So what happens to a positive charge in that spot? And that's why lines move away from positive charges and towards negative charges, because positive charges repel other positives, but negative charges attract other positives. Does that make sense? We'll talk about this a little bit more in this outline too. All right. So for the next couple days, we want to talk about, or I want to talk about, I don't know if you guys do, but if you want to do well on your test, you might want to talk about it. These four terms right here, electric potential energy, voltage, current, and resistance, which I think are terms that some of you are at least familiar with. You've heard them before, but you might not understand what they mean, right? So in order to help you understand what they mean, we're going to make some parallels to things that hopefully we already know. And it starts with this picture, okay? All right, so don't blink, everybody. If you blink, you're going to miss the best thing you're going to see all day long, all right? So, yellow object, let's say it's this object if we want to, okay? Green things always represent the Earth to me. And so let's say we take this object and do this, okay? Let's parallel things that we've already talked about. From an energy standpoint, what happened to the energy of that object? As we move it from the ground upward, what happened to its energy? It gains potential. Specifically, what kind of potential? Gravitational potential, right? So, what happens to gravitational potential energy? It would increase as we move it upward. Was work done on the ball to make that happen? Yes, because work changes energy, right? So I think if you check out your outline, those might be your first two questions. Yeah. Oh no, not yet. So okay. Oh yeah, you have a little picture on the side. And we said this is true of all kinds of energy. If it gains potential energy, what is it eventually looking to do with that potential energy? Change it to kinetic or somehow get rid of it, right? So if we let it go, right? Don't blink. Ready? Here we go. Up. Oh yeah, look at that. I don't know how this could not enhance your understanding like 100-fold, right? This moving object. Right? So as it falls, what happens to its gravitational potential energy? Decreases, but what happens to its kinetic energy? Increases due to what? What do we call this concept? Conservation of energy, right? One energy goes down, the other energy goes up. Okay? We're all clear with this, yes? Right, we talked about it like a ton of times. Now, let's apply this to some other situations. This happens because we move this object, this yellow object, around in the gravitational field of the Earth. Which way did we say that the gravitational field points? Gravitational fields always point towards the middle, right? So as we move it upward, we're moving it against the field. Yes? Right? The field points down, we move it up. If we move it against the field, what happened to its energy? Well, when we move it up, what happens to the energy of this object? It gains potential. And as it moves with the field, as it moves downward, what happens to its potential energy? It decreases, but we see an increase then in kinetic. All right? Good there? All right. Keep those ideas in mind as we go forward. Electric potential energy. Electric potential energy is the energy of a particle due to its position within an electric field. Okay? So I think it should start getting into your outline right now, right? What's gravitational potential energy? Parallels, right? According to this definition, how could we modify it to be a definition for gravitational potential energy? Come on. Make the parallels, everybody. Yes. Eric said due to its height. Let's go. Height deals with what now? We talk about it more generally. The position or the energy due to its position within a gravitational field. Okay? Gravitational potential energy and electric potential energy are very similar in that they deal with position. Okay? Electric potential energy, EPE, I'll abbreviate it that way from now on so we don't have to write it, is a form of mechanical energy, just like gravitational or elastic potential energy. When a charged particle is moved within an electric field, work is done, and the energy of that particle changes, just like when we move it up and down in a gravitational field. Okay? Good so far? All right, let's take a look at this picture. Okay? So, over on the left-hand side, bunch of positive charges. Over on the right-hand side, a bunch of negative charges. Which way do the arrows point? From positives to negatives, right? Because that's the electric field. Okay? This yellow represents a separate positive charge. This is where it will settle on its own, right? Because what do positive charges do to other positive charges? Repel, and negative charges attract those positives, right? So if we leave this yellow object, which has a positive charge, by itself, it moves to the right. Yeah? Will it do that on its own? No. But work is done. Okay? Work is done as we move this object against the field. Yes? Okay? So, when work is done, what happens to energy? It transfers. In this case, is the energy going to increase or decrease? Does it like being there? No. We said places where things don't like being, they have a lot of energy, right? Because they're trying to get rid of it. In this case here, right, the electric potential energy is increased. Why? Because what did we move it closer to? A bunch of other positives. Does it like being there? No. It would rather be over here by the negatives, right? So, the next question that shows up, three ways that electric potential energy can increase by changing positions, right? First, if we move positives closer to other positives. That's one way we can increase the energy. Good there? Next, right? Let's say that this side over here, where all the positive charges are, doesn't exist. Would that change the way the arrows are going? Because positive charges like to get away from other positive charges, but they also like to go towards negative charges, yes? So, we can move positives closer to other positives, or we can move positives farther away from negatives. Because positives and negatives like to be close to each other, right? So we can move positives closer to other positives. We can move positives farther away from negatives. Right? Good there? Yes, no, maybe? All right. Let's talk about the third one in just a second. But let's talk about this situation. So we've increased the electric potential energy because we moved this yellow object, which has a positive charge, against the field. If we let it go, what's going to happen? Well, it's going to go to the right. As it goes to the right, what happens to its potential energy? It decreases. But what has to happen in response to that? Kinetic energy increases, right? Just like when we move something in the gravitational field. It's exactly the same idea, just a different kind of field. Okay? Good there? What if I do this? What if I move it perpendicular to the field? Anything change? What if I move this object from here to here? Does it have any more or less energy? Moving objects perpendicular to fields doesn't change anything about its energy. So your next question, right? How can a positive charge move in the field without changing its electric potential energy? How does it have to move? Perpendicular to the field. Remember, these arrows represent the field, the area that it can change other objects. Okay? Good there? Yes, no, maybe? Okay. Let's go this. So, when work is done against the electric field, electric potential energy is increased. Okay? Did I leave you guys a space to write this? God. I should have left you a space to write this. Okay? This is probably something you need to know. When work is done against the electric field, electric potential energy is increased. Just like when we do work against the gravitational field. That's just a fancy way of saying, right? Doing work against the gravitational field is just a fancy way of saying moving an object which way? Up. Right? Doing work against an electric field means you bring positives closer to positives. What else could it mean? Well, if we do work against the electric field when positives come closer to positives, what else could you do? Negatives closer to negatives. right? Because what else will they do? What will they do to each other? They repel, right? We also talked about that what else could you do with a positive and a negative? Move them how? Well, where do they like to be? Close, right? So if we move them how? If we move them away from each other, that's doing work against the electric potential field, or against the electric field, right? We want to bring positives closer to positives, negatives closer to negatives, or positives away from negatives. Any of those would increase the electric potential energy. So, on your three things, right? We talked about positives closer to other positives. We talked about positives farther from negatives, but we could also do negatives closer to other negatives. Any one of those would increase the electric potential energy. Those charges don't like these things to happen. That's doing work. They won't happen on their own, but if we make them happen, that's an increase in energy. Right? Good there? Okay. The particle now has more energy, more ability to move or change matter by virtue of its position. Just like I'm going to take this ball and move it upwards. Now it has more ability to hurt my foot when it lands on it than it did down here. Right? Work against a field increases energy. Good there? So, let's take a look at these two pictures. Okay? Strong electric field, weak electric field. Which one's going to increase the energy more if I move this particle to the left? Strong field, right? So, for the last two questions, or for letter F, two other ways that electric potential energy can increase other than changing the position. What can we do to the field strength? Stronger field, right? Just like when we go to the moon, what happens to the gravitational field surrounding the moon compared to Earth? It's a smaller field or a weaker field. And that means not as much energy. Right? The last thing we could do, and I don't know the picture of this one, right? What if we make this yellow charged object have twice as many charges? Right? If it's 1 plus sign, it's 2 plus signs instead of 1 plus sign. Moving 2 plus signs closer to other plus signs. That increases energy as well. So the last way for letter F is we can increase the charge. Any one of those would increase the electric potential energy. All right, do we understand this? Or at least kind of, sort of, maybe. It's real similar to gravity, other than it's electric fields instead of gravity. Okay? Good there? All right. Let's stop it there for today. We'll discuss voltage and current and resistance tomorrow in class. Don't forget, open note quiz tomorrow, overcharge, force, and field.